I was listening to this podcast episode recently on databases, and they started talking about the CAP theorem. Now, if you're anything like me, you've heard of CAP before, but never really dug into it because it always seemed like this kind of abstract back-endy concept for database nerds. I mean, just listen to the Wikipedia definition. In theoretical computer science, the CAP theorem states that it is impossible for a distributed data store to simultaneously provide more than 2 out of the following 3 guarantees: consistency, availability, and partition tolerance. Well, it turns out that the CAP theorem is way more important for front-end development than I realized. And that's because CAP is actually not about databases at all. Let me show you what I mean. Let's say we're working on our To-Dos app. And this is a JavaScript app right here in the browser. And of course, this is talking to an API server over here across a network. And now when everything is kind of humming along and the network's up, our users can create new to-dos, they can fetch to-dos and delete to-dos, all the normal stuff, and the UI remains responsive and up to date. But what happens when the network goes down? Let's say our user hops on the subway and they lose their network connection. Well, now we have a decision to make in the UI, right? And we can basically do one of 2 things. The first thing we can do is show them a dialog that says, there's been a problem, we don't have the internet, and you're gonna have to come back later and try again. And the second option, which is a little more sophisticated, would be to let them kind of continue making to-dos and maybe even editing to-dos and maybe even checking them off and telling them that the network is down so their changes will be saved later, and then maybe once they get off the subway, we can go ahead and replay those actions for them. And maybe we do that using local storage. And that's it. You just learned the CAP theorem. Don't believe me? Check it out. You see, our API and our UI here are 2 parts of our system. And this network failure right here is sometimes called a network partition because part of our system has been partitioned off from the rest of the system. So in the event of a network partition, if we want to tolerate such a situation, if we want our system to do anything useful at all, we have these 2 choices to make. And the first is to not allow any new reads or writes, to just tell the user to wait here, since we can't give them, 100% accurate view of the world, and only when the network comes back will we refresh their data. And this option exhibits consistency, since it's emphasizing this consistent view of the world. And over here in door number 2, we keep the UI responsive to our users' actions, even if that means that their data is going to be different from what is actually on the server, right? If they are creating and deleting to-dos while they're on the subway and someone else opens up the app somewhere else in the world, they might see different data. So this option is exhibiting availability since our user is able to keep using the app. And this C, A, and P are what constitute the CAP theorem. Now, if you remember from that nerdy definition earlier, the theory says that we only get 2 out of these 3 characteristics at any one time. So why is that? Well, these 3 conditions, consistency, availability, and partition tolerance, these are all desirable, right? We want all of these 3 things. But the problem has to do with the network. And in the real world, all networks fail. I mean, that's basically all there is to it. So if we want our system to keep doing anything at all, then we need to have partition tolerance. So the P is more or less a given here. And when we're talking about a world where there has been a network partition, we're back to the world where we have to make a trade-off between consistency and availability. If we choose consistency like we did in 1, so 1 would be here between C and P, then we're saying we're only ever going to show accurate verified data to our user. That means we have to sacrifice availability and reject any new reads and writes that our user makes, while they're on the subway. But if we choose availability, so let's say we have this optimistic UI here, which would be kind of along this axis, then we sacrifice consistency. because the user is now effectively working with a replicated version of the data on their device, and any replicated data set is at risk of falling out of sync with the original source. And that's what CAP is all about. You get to choose two, but you can never have all three. So why is CAP usually talked about in the context of databases? Well, what CAP is really about is data replication. And as we saw in our example, the problem started arising when we had copies of our data between our API and our UI. And that's when the implications of CAP start to matter, and that's when you have to start making trade-offs between availability and consistency. And on the database side, data replication comes up when you need to start scaling your database server. And this is going to look really familiar. You start with a single database here. Let's say it could be, an SQL database like Postgres. And this guy has all of our to-dos in it. It has to do with ID 1, to do with ID 2, all the way through to do with ID 1000. And this database is both consistent and available as long as it's online. It's consistent because every read and write goes to this primary node here, which is the only source of data, and it's available because as long as you can talk to the DB, you can read and write to it. So it's C and A, but it's not P. It's not partition tolerant because if this node goes down, well, there's only one node, so the whole system goes down. So if you ever want to tolerate a partition, well, you need to have a second node. And these two nodes are going to communicate via a network of some kind. And now you have a decision to make, which is how are we going to split up these 1,000 to-do records between these two nodes? And again, we've basically got two options. Option 1 is to put records 1 through 500 in this node, and then in our second node here, we'll put records 501 through 1000. So now we have a network between these two things, and let's say that node 1 suffers a partition. Well, our system can handle it. The whole thing doesn't go down, so we are partition tolerant. But if reads for records 1 through 500 come in, we can't respond. So we don't have availability, right? But if a read or write for 501 through 1000 comes in, then our system will be able to handle those requests with fully consistent information. So we do have C here, and we do have P, but we do not have A. Alternatively, we could replicate our data. And so we'll draw our two nodes again right here. But instead of splitting up the data between them, we'll just copy it. So this will have 1 through 1000, and this will have to-do records 1 through 1000. And so now let's assume that node 1 here suffers a partition, but node 2 is still online. So if any read or write requests come in, we can actually handle that because node 2 has all of these records. And when the partition goes away and the network comes back online, we can propagate those changes back to node 1. But we have replicated our data, and as we learned before, anytime we have data replication, we suffer consistency, right? Because when things are working normally, let's say a write request comes in and it goes to node 2 here, well, node 2 might have to update one of its records, and because this is a real-world network here, there is some latency between when node 1 will receive those changes, and in the meantime, if node 1 were to get a request for that updated record, it might potentially serve stale data. So that's basically the risk whenever you replicate data, which is why this system is available and partition tolerant, but it is not consistent. So we see the exact same trade-off being made here, where in the event of a network partition, you have to make a trade-off between consistency and availability, the CAP theorem. And different database technologies will make different trade-offs based on what their needs are. So again, we can only have two of these three things. So if we were to draw lines between them, all the databases must live on one of these lines. And there's ways they can move around them, but at any one time they have to be on one of these lines. And traditionally, SQL databases live over here, things like MySQL and Postgres. These are going to be CA systems. They're consistent and available because, again, going back to our original example, when they're online, they are going to be serving consistent information and not sacrificing any availability, but they are not by default partition tolerant. Now, NoSQL databases like Mongo are CP systems. They're built to handle partition tolerance kind of by default, and they give you strong consistency while sacrificing some availability. And databases like Dynamo from Amazon are also partition tolerant, kind of by default, but they sacrifice some consistency for the sake of very high availability. And you might hear these sorts of systems that live on this line referred to as eventually consistent for this very reason. The reads might be stale, but the system is always available. And which trade-off you make for your database comes back to the question of what application are you building in the real world. Take Dynamo, for instance, which was built by Amazon. If you're checking out on Amazon.com, what's more important? That you can click checkout and see an order confirmation page, and then maybe you go to My Orders and you see a stale list of orders that doesn't include that recent one. You wait a little bit, you refresh, and it shows up. Or is it more important that Amazon.com always shows you the most accurate, consistent data, even if it means trying to check out and having a message say the system's down? You can start to see why Amazon would probably want to favor availability here to never interrupt the user checking out over consistency. And that's exactly what Dynamo is built for, and is actually the case for a lot of websites, which is one of the reasons why these eventually consistent databases have become so popular. Now, bringing this back to front-end web development, we have to make these exact same trade-offs too. We have to decide whether to prioritize consistency and showing our users accurate data, or availability and letting them take an action no matter what. In some apps, it might make sense to prioritize consistency. So in the event of a network failure, maybe we shouldn't let users book a seat on a flight or in a movie theater because when the network comes back on, we'll have overbooked the flight. But a lot of the times, the best UIs are the ones that favor availability at the expense of some consistency. I mean, just think about all the apps you use on a daily basis. Things like your Notes app or your Mail app on your phone and your computer. You know, you can send messages or update notes even if you don't have a network connection. The app will do the best it can to retry your action on your behalf once the network is restored. Chat apps like Discord and Slack show you a lot of information, even if those messages could be stale if you have had a network partition. And they even let you kind of send messages and retry them once the network comes back online. And there's an attempt to make all of these core interactions available to you in spite of a network failure. And these sorts of optimistic UIs generally result in a better user experience than just showing a message that says the network's down, try again later. But there's no doubt that consistent systems are easier to build and reason about. So if you're going to build an app with high availability, just know what you're getting into and make sure the complexity is worth it. Now, there's actually a highly available distributed system that you probably use every day without even realizing it. Git. Git is a distributed system with a replicated data store. Copies of the repo live on your computer and on GitHub or other Git servers. And Git favors high availability interactions. So almost every interaction within Git you can perform locally, even if you don't have access to the network. But when it comes time to do something like Git push back to origin, that's the situation where you need to have the network present. But you can see some of the trade-offs that are made. Because the system favors availability, it allows for potentially conflicting reads and writes. And so when the network comes back on and you push your changes up to origin, you might have a situation where you need to merge a Git conflict. And this is the kind of complexity that comes from building highly available systems. But it also enables this really incredible tool that is an indispensable part of our day-to-day workflow as developers. So you see, CAP really shows up anytime you have a distributed system and replicated data. A cluster of database nodes is a distributed system, Git is a distributed system, but so are many of the apps that we use and work on every single day. And you see apps like Slack or Google Docs make very different decisions regarding the trade-offs between consistency and availability. But even Slack and Google Docs, with all their resources, can't violate this physical limitation of the universe, and they have to make that trade-off. So that's the CAP theorem. That's why it matters to you as a front-end developer. And the next time you walk into a room full of back-end engineers, instead of referring to yourself as a front-end developer, I know, right? I'm so sick of dealing with CSS. Just call yourself a distributed systems engineer. I know. That CAP theorem really keeps biting us in the ass, doesn't it? And you might just start getting that full stack respect you deserve.